Stop! Did you know that there's around 3 grams of microplastics per 200,000 liters of water in Lake Okanagan? Now you're thinking, that doesn't seem like a lot, but that equates to more than 436 tons of microplastic. Considering the lake is a primary water supply for the city of Kelowna, you're drinking about 0.05 milligrams of microplastic per day.
Sup, fellow students? I'm Arthur.
I'm Jasleen. I'm Lien.
And I'm Liza.
And we present to you our project of microplastics on Okanagan Lake.
Our goal is to reduce the amount of microplastics in the Okanagan Lake. The lake has over time aggregated high quantities of microplastics, which has further contaminated the habitat. This problem leads to many proven health issues, as well as the contamination of the flora and fauna of the lake and surrounding areas.
An effective method for extracting microplastics is necessary for the safety of the environment and health of Okanagan residents. This will lead to safer water and a reduction in the amount of plastics found in the surroundings.
In our solution, we aimed at meeting 5 different specifications to have our project working. Meeting the 5 specifications would mean what? It means meeting efficiency, it means meeting maintenance, sustainability, durability, and cost. With our solution, at the end, we found that it's gonna clear 95% of all the microplastics.
We bring to you the ROBO fish. This filtering robot is an effective and efficient way at reducing microplastics.
The fish contains a multi-layer membrane filtration system and reverse osmosis filter, which is capable of filtering out 99.4% of microplastics. Built out of PET plastic and coated in a thin layer of silicone rubber for durability against water pressure and sustainability, this fish would weigh approximately 372 grams in total with a 20.6 centimeter wingspan, 20.5 centimeter length, and a height of 11.5 centimeters. For movement and flow rate, the fish will have 3 propellers that will spin to generate a small amount of energy for sustainability.
Its back tail will be necessary for steering, and its 2 fins will allow the fish to move in 3D directions. For user-friendly design, the RoboFish has LED lights to indicate whether it is powered, and a removable panel for easy maintenance.
To reach a realistically working prototype, we had our robot pass through 3 different tests.
First, the material test. We compared PET, HDPE, and rigid PVC to see which material would be strongest for the frame underwater. Each material was modeled in SOLIDWORKS as a 50 by 50 by 2 millimeter plate, with the sides fixed and a pressure of about 19,620 pascals applied, equivalent to 2 meters depth using the hydrostatic equation P equals rho GH. SOLIDWORKS gave us stress, displacement, and strain plots. PET showed the best mechanical performance, highest strength, and lowest deformation. Its downside is microplastic fragmentation, which conflicts with our filtration goal. To prevent this, we plan to coat the PET frame in a thin layer of silicone rubber, keeping the strength while avoiding fragmentation. Second, the filtration test. We isolated the filtration module and modeled a 3-stage system, micro, ultra, and nano, inside an elliptical cylinder. Each porous layer was given pore size-based flow resistance, and we ran a steady-state simulation with a 10 kg per second inlet flow. The main focus was pressure distribution. The results showed smooth, even flow and a predictable pressure drops at each layer, especially the microfiltration stage. This confirmed that the triple mesh design supports efficient, uniform filtration.
Finally, the electrical and propulsion test. Since we're not physically testing it, we used the specs of our 7.4V Litchfield thruster to estimate thrust, speed, and battery life. The model predicts about 1.81 newtons of thrust and a top speed of 0.63 meters per second. Efficiency stays fairly high between 5 to 10 watts. However, it does drop at higher loads, which does limit the battery runtime. These results then give us the electrical performance baseline we need to choose realistic power settings and battery capacity before actually doing the physical prototype.
Although the RoboFish is effective in many aspects, the cost of developing our solution remains a barrier. This being said, its application holds potential for yielding long-term economic returns as well as help build a more sustainable future.
Thank you for watching!